Hi class. Today I'm going to walk you through one of the more difficult EMR problems I could ask for you to do on a quiz or a test. Now the first thing I do before I even read a problem is just write the equations down that might be involved in it. So there are two equations we've been talking about this unit involving energy and wavelength. So the first one that I should know is that the energy of a wave is equal to Planck's constant times the frequency of that wave. The second equation I should know is that the speed of light is equal to a wavelength times its frequency. Now, I always know h and c because they are constants. H is equal to 6.626 times 10 to the negative 34th joules times a second. Remember, this is like the quanta amount of energy that a wave, or not a wave, but that an object can get at a time. C is equal to 3.00 times 10 to the 8th meters per second. So right off the bat, those are check marks that I can make. So I'm going to read this problem. So in a bright line spectrum emitted by hydrogen gas, a red line with a wavelength of 656 nanometers and a green line with a wavelength of 486 nanometers are observed. So I know that I have two problems I have to do right off the bat here because I just got a wavelength for red light and one for green light. So those are the same variable, which means I have two problems to solve for each of these things. So both lines are formed as electrons move from higher energy levels to energy level 2. The first question here is saying, well, what line has the largest energy change? So there's a couple of ways you can approach this. You can solve the whole problem all the way through for energy and realize that, yes, green's going to have the higher energy and then go back and answer A. But another thing you could do is know that this never changes. C is the same answer over and over again, 300 million, so 3 times 10 to the 8th. If I have a higher wavelength, like the red light does, right here, that means my frequency has to be low. If I have a smaller wavelength, my frequency has to be higher because they both need to multiply to this number. So they are inversely proportional. So a smaller wave has a higher frequency. So if I take that frequency over here, the one with the higher frequency will have a higher energy because H never changes. So if frequency is high, then energy has to be high. If frequency is low, energy has to be low. So just looking at that problem for question A, the green light has more energy. So that's the way you can do it if you're just reasoning through the problem. But if you can't do that right off the bat, you can break it down a little further. So let's say I don't want to sit there and reason that through, so I'm coming back to A even though, yes, I just answered it. So part B is saying, well, what are the energy differences between the higher energy levels and energy level 2? So that's saying, like, hey, here is the center of my hydrogen atom, and I had a, here's my rings, sorry, so here's energy level 1, energy level 2, energy level 3, and so on and so forth. I guess I should draw at least one more. So let's say that I fell from green from 3 down to level 2, and that was the green light that I saw. Well, that wave has energy. Maybe the red light fell from 3 to 2, and that emitted the red light I saw, and that has energy. So you're just essentially solving for the energy of each wave. That's all it's asking. So the energy difference between whatever level it was at doesn't have to be 4, it could have been higher, down to 2. The energy that it emitted when it fell from, again, doesn't have to be 3, but down to 2. You won't find the actual energy level it was at, but you can find the energy change between the two levels, and that's the E over here. So I'm going to try to erase this real quick, and we will work on the problem. So you can start this one of two ways again. So just pick a wavelength and solve for the frequency and then find the energy. or just find the frequency of each, then find the energy of each for part B here. So I'm just going to work all the way through red and then all the way through green. So I'm going to start with green. So right now I know the wavelength is equal to 656 nanometers. I know the speed it's traveling at, and I know Planck's constant. The only equation that I have enough information to solve is this one right here, to solve for my frequency. So if I rearrange that equation, I know that frequency, oops, wrong marker there, frequency is going to be equal to the speed of light divided by my wavelength. And both of these are things I know. When I'm looking at this measurement, it is in nanometers. The conversion factor from a meter to a nanometer is that a nanometer is 10 to the negative 9th. So if I want to convert this to meters, 656 times 10 to the negative 9th would be my meters. So that would be my wavelength. So I'm going to solve for my frequency of my red light. So I'm going to have the speed of light, because obviously it's light, it's traveling at the speed of light, and it's going to be divided by the wavelength, 656 times 10 to the negative 9th nanometers. Make sure, if you plug this into your calculator, that you put parentheses around each of these terms. Otherwise, depending on your calculator, it might try to do something weird with order of operations. We can also do a quick, oops, that should be meters, not nanometers. We should do a quick unit check though. So if I have a meter over a second divided by a meter, well, this crosses off, but this is still on the bottom of a fraction, so you have 1 over a second, which we call a hertz. So that makes sense because we are solving for a frequency. So I'm going to erase this and then we will solve the problem. Once I plug this into my calculator, your energy should be equal, or your frequency rather, should be equal to 4.57 times 10 to the 14th hertz. So I just found frequency, which I now know over here for my red light. So what can I do? Well, I can solve for my energy of my red light. So I'll switch to black just to make this a little bit easier. So I'm going to just plug in the numbers that I know. I know Planck's, I know my frequency now. I can solve for the energy of that red light. So the energy of the red is going to be equal to Planck's constant, so that's 6.626 times 10 to the negative 34th joules times a second, times that frequency we just found, which was 4.57 times 10 to the 14th hertz. When I plug that into my calculator, I should get 3.03 times 10 to, oops, that should be a 10, excuse me, 10 to the negative 19th joules. And if you want to do a quick unit check, you have a joule times a second times 1 over a second. So your seconds cancel out, your unit should be joules, and that is a measure of energy. So I've rewritten the things we just found just in the interest of saving space here, but now I need to do the same thing for the green light. So I know the wavelength, I don't know the frequency, which means I can't just immediately solve for energy, so I've got to do the same thing. So I know the frequency of my green light is going to be equal to the speed of light divided by the wavelength that it emitted. So that is going to be the 3.00 times 10 to the 8th meters per second divided by that wavelength, which we need to convert from nanometers to meters, so that's the same type of conversion, so 486 times 10 to the negative 9th meters. When you do this, again, make sure that you are plugging in with parentheses, or else you will not get the correct answer. Your calculators tend to like to do weird orders of operations, so parentheses those numbers off, and you should get the right answer here, which is going to be 6.17 times 10 to the 14th hertz. So I have found my frequency now. I know Planck's constant. Same thing for the red light that we did. The energy of my green is going to be equal to Planck's constant, that's 6.626 times 10 to the negative 34th joules times a second, multiplied by that frequency we just found, 6.17 times 10 to the 14th hertz. And when you plug that in, again, use your parentheses, but when you plug that in, the energy you get should be 4.09 times 10 to the negative 19th joules. So looking at the two energies I just found, what one's higher? Well, the bigger number. They both have the same exponent, so I'm just going to look here. 4 is bigger than 3. Green is higher in energy, just like we talked about earlier. So for the last part here, C, what's the difference between the two higher energy levels? So I don't know necessarily like what ring each of these things fell from to get to energy level 2. I know green definitely came from a higher level than red did. So what's the difference between those two energy levels? Just subtract it. So just do, for part C here, let me change colors. So for part C here, you're just going to subtract your energies. So you're going to have 4.09 times 10 to the negative 19th joules minus the 3.03 times 10 to the negative 19th joules. And that should get you 1.06 times 10 to the negative 19th joules. So it's saying whatever energy levels these two fell from, this is the amount of energy between those two levels. We don't know what two levels necessarily that they started at, but this is the difference between those two levels. I hoped this helped. Have a good night.